Hi, I'm Rafaela.
I'm Justin,
And I'm Jenna.
and we are the Unit Process Analysis pH subteam.
So our subteam wanted to explore the performance of the Agua Set tank as a function of pH. So this basically meant that as a team, we wanted to keep the coagulant dosage to a constant amount, and this is different from our prior designs where the pH probe was actually quoted in the coagulant dosage, making it very difficult to measure the accuracy of the set tank.
So just a brief introduction of the set tank, which is short for the sedimentation tank. On the left, we have a common blueprint of the model used within industry, and on the right, we have our lab scale model. So there are three main parts of the sedimentation tank that we're going to be modeling. We're going to be modeling the flock blanket, the sedimentation plates, and also the flockware. So first off, we have the flock blanket. And the flock blanket is essentially going to be the area where all the flocks collide with the contaminant in order to filter them out from the effluent. And essentially this is going to be represented by the vertical height within our lab scale model. Next we have our flockware, and our flockware is essentially going to be a way to limit the height of the flock blanket. And the sludge shown within the left figure is essentially going to be our clay contaminant. And the hopper purge valve on the bottom left of the left figure is going to be represented by the waste stream. And finally, we have the sedimentation plates. The sedimentation plates are going to be a way, a last resort in order to prevent the contaminants from any more contaminants from escaping the set tank, because the sedimentation plates are going to be a part that disrupts the flow and essentially allows the flocks to remain within the set tank, and that's going to be represented by a kink within our system.
So this is our current system blueprint. So walking you through this, first we have the clay stock and the water stream that is pumped within the system and mixed together into the effluent turbidimeter, and this is just to take the purity of the incoming water. Then we have that mixture mixed with the coagulant dosage and the acid-base stock, and then these two mixtures are then sent into the flocculator. After that, it's then pushed into the sedimentary tank, where it's pushed into the effluent turbidimeter, and then the pH is measured, and that's to take the purity of the filtered water. One thing I wanted to say about this blueprint is that we actually have the clay pump placed before the effluent turbidimeter. Not only that, but we took out all our bypass pumps because they were unnecessary. And then we also have the waste pump placed after the flockware here. And this is because we wanted the waste pump to push all the outputs from the flockware into the effluent turbidimeter. This is different because prior to this, we had where the waste pump was actually more in between the effluent turbidimeter and the flockware. And then this caused a lot of backups within our system. So here we have our original setup. And this is basically the setup that the flock blanket used to get our controlled experiment. And in this setup, we were able to figure out our ProCoda methods, making sure that it was correct. We also used this to, this was also different because this doesn't have an acid-base pump, nor does it have our pH probe here. We also use the system to check for any leaks in here, making sure that we were able to use this and make our system better.
So our current setup deviates from our system blueprint in that it, where we measure the effluent pH, we moved it because before the stream from the flockware was in the waste stream, so there was all this sludge going in, and we don't really want to measure the pH of the sludge, we want to measure the pH of the clear water. So we moved where we would measure the pH to right after the top of the sedimentation tank. And it also deviates in that we removed some of the bypasses because we didn't really need any bypasses because we had them in originally because we thought, oh, maybe our system would get blocked and there would be some blockage in the system, but we found that this wouldn't really happen, so we found it unnecessary to have all of these bypass streams. And then at first our bottom geometry that we had found in the lab was it was flowing upward with our sedimentation tank, so we decided to 3D print a new one with a non-porous material. but this was still not enough, so we had to put tape around the bottom of it so that it would stay at the bottom of the sedimentation tank. And while we were printing it, there were some complications and parts of the sides got damaged, as you can see in the photo here. But this didn't change the effectiveness of the bottom geometry because the fluid would still flow through the bottom geometry as needed.
And after setting up our apparatus, we still needed to find a way to control the whole system, and that's where ProCoda came in. Essentially, ProCoda is a way to control our pumps and also be able to read information from the system. And for example, each pump would be essentially connected to a different address, and we would essentially be reading and also giving the pumps signals, such as signals to change the pump speed depending on the state of the system. So for our system, we had two states. We had either a run state or a warm-up state. The run state essentially was where we ran water through the system, essentially just cleaning out the system of any previous contaminants. And the warm-up state is essentially going to be the area where we are running water through the system and cleaning out the system of any previous contaminants. And the run state is going to be where we are adding in the coagulant, the clay, and the acid-base stock solution into it. So since our goal is to measure the pH of the system, is to measure the effluent turbidity at some pH within the system, we would of course need to be able to control the pump speed of the pH pump to a particular pump speed, in which helps maintain the pH levels within the system. So to do that, we use PID, which stands for proportional integral derivative, which is essentially a way to maintain or reach some desired speed, depending on the current pump speed, which is going to be the error. And finally, we have our stirrer and turbidimeter. Prior to this, we manually controlled the stirrer. However, we realized that if we manually control the stirrer and then the system stops running, there will be a huge mess on the table the next day.
So what we've done so far is we set up our sed tank model. So we connected the flockware to the sed tank, and we also set up our entire apparatus with a pH meter, pH stock, and all of the pumps. And then we connected all of those pumps and made our set points and connected everything through ProCoda. And we also printed our bottom geometry, as I said before, and we ran water completely through our system. So some setbacks that we had was, before finishing our setup, we had trouble connecting the flockware to the sed tank. So we started out trying to melt plastic to connect the two together, but melting the plastic took too long. We waited about 2 hours and the plastic had barely melted. So then we attempted to ask employees in the CEE lab to help us, but we were unsuccessful. And then we finally decided to use PVC cement to glue the flockware to the sed tank, and this worked. And then when we were trying to first run water through the system, we forgot to attach part of the turbidimeter that holds the water. So water ran completely through our turbidimeter, and we thought that it had broken completely. So we took the turbidimeter apart and dried everything, and then left it out for a few days. And then after a few days, we reassembled it, and it worked as needed. So there wasn't any water damage, so we got really lucky with that. And there were also leaks in our apparatus when we were running water through the system. So we attached tubings tighter than before, and we had to replace some of the tubings. And our bottom geometry wasn't staying in place, as I said before. And then after running water through the system, ProCoda crashed because our set points were off by like one place. So we had to go through all our set points and make sure they were in the right place. And after that, running water through the system with the ProCoda methods, it all worked out.
So looking forward on this project, we still need to finish the rest of the setup, which includes adding in the pH and the clay pH, clay, and the coagulant stock solution, and we still need to find a better way in order to measure the pH of the system. And since we haven't been able to run the system with any acid base, coagulant, or clay, we aren't exactly sure if our method currently works. Our method currently is to actually have a bottle that would store some of the effluent, and it's going to be up to some level in which we are able to read the pH and let ProCoda do the data analysis. However, and then just simply have another hole out of the plastic bottle going to the waste. However, we aren't sure if this method would work, because this would have to be assuming that we can actually reach a certain water level within the plastic bottle, and this is also assuming that the plastic won't possibly overflow, or the flow rate is equal to the flow rate out. And after that, we still need to debug the system. We still need to figure out an optimal concentration for the pH and clay, and coagulant stock solution, because we do not want the pH, clay, and the coagulant stock solution to essentially run out prior to getting any useful data, or prior to the flock blanket actually breaking down, because that is what we want to measure. How long essentially the system can last prior to failing to filter out the contaminant. And after that, we hopefully want to run the system and then analyze the data. In the end, the goal is to achieve some target pH and then measure the performance of the system.